Hey, what's up, guys? Chung here again. And this time, let's take a look at another LeetCode problem here. Media level, coin change, number 322. Okay, so this is like a very typical DP problem. So you're given like a coins of different denominations and the total amount of money amount. Write a function to compute the fewest number of coins that you need to make up that amount. If that amount of money cannot be made up by any combination of the coins, return -1. Okay, so basically you're given like, for example, you're given like a coins with the with 1, 2, and 5 as as the denominations, and the total amount is 11, right? And so the minimum amount we need to make up total amount 11 is 2 fives and 1 1, right? Even though we can also make up 11 with like several twos, right? And another one here, but 3 is the smaller number. That's why we take 3. Okay, so I mean this is like a little bit of a variation of the complete K-knapsack problem. I think you guys maybe have already known the basic idea of the K-knapsack problem. Basically, there's like a 0 1 knapsack, right? And then there is like complete knapsack. So and for the very basic problem for 0 1 knapsack, basically you are given like a few items, and for each item you can only choose it at most once. Basically, you either choose it or you don't choose it. But for the complete knapsack problem, and basically you're given like you can choose as many as you want, as long as it didn't exceed the capacity. In this case, it's the amount. Okay, and for the original complete knapsack problem, it asks you to find the with this like capacity limit, what's the max value you can get, right? It asks you to get the max value. So in this case, it asks you to get the smallest, basically the smallest number you can get, right? The smallest number of this smallest number uh, of the coins you need to make. Okay, so I think the only difference with this between this one and the original complete knapsack problem is the definition of the DP. Okay. And okay, so I will try to write the very basic 2D arrays complete knapsack solutions, and from there we can try to optimize it from 2D to 1D. Okay, and cool. So for the 2D problem, right? So for the 2D problem, we're gonna have like an n, so to the length of coins. Okay, and for the DP, right? So for the DP, basically the first dimension is the coins, right? And for each of the coins will be basically will be looping through all the amounts. Okay, that's why for at the beginning I'm gonna the okay. So the second the second dimension is amount +1, right? And for and the first like dimension of DP is the number of coins. Okay, and okay, and since it in this problem it asks us to find the minimum, the minimum value, right? So in this case, we initialize the max size, we initialize everything uh, to the max number first, okay? And then for the DP 0 and 0, right? So we need a base case, and for the 0, which means without any coins, and for the amount, right? For the current amount, for the 0 amount, obviously the base case is 0, which means we need we need 0. That's our base case. Okay, and then we just loop through the coins, right? The coins is n 1 to n plus 1. Okay, n plus 1. All right, so the coin value is the coins uh, I minus 1, since this I represents the number of coins. And in this case, since we already take care, we don't care about 0, we only care about for 1, starting from the first coins. Okay, and then from the first coins, the J is the range from the the is for the amount, right? For the amount plus 1, basically, because we want to also consider the amount itself, right? So what does this mean? So basic the basic template for the complete knapsack problem is for each of the coins here, right? Basically, we have two options. We either take this coin or we don't. Okay, so if we don't, okay, so if we don't take the current coin I here, the DP I here, basically the DP IJ here, IJ means to the minimum coins, uh the minimum coins to get to J amount, right? After after considering, right? Considering first ith coins, right? Basically, that's the definition of this 2D DP array. And this is like a normal definition of the knapsack problems. Basically, we always define the I is the after seeing the first k element, right? And J is the to get with the current capacity, right? In this case, is the amount is our capacity, right? And what's the minimum? Because in this problem, it asks us to find the minimum coin numbers. Okay, so now for this 2D DP here, and the first case is we do not take, right? Do not take ith coin. That's the first case. Okay. Mm, yeah. If we don't do not take the ith coin, then we do what? We do a since we are looping through all the j's. That's why we have to do it for all the I and j as well. So basically, the I and j equals to dp I minus 1 and j, right? So what does this mean? It means that the minimum number, since we didn't take the ice coin, right? So the minimum number for us to get to the current j uh, after seeing the first ice coin is equivalent to after seeing the first I minus 1 coins, right? And to same j here, because we didn't take the current I. That's why we can use this one. And the second uh, yeah, I and j. hmm So, and the second case is we take the current I. We take the current I here, right? That's why since we're starting from the j here, but since we're looping through from 0 to amount I plus 1, that's why we have to do a simple check here, because we only can go back to the previous state if the current j is either equal or greater than the coin itself. Why is that? Because I'll show you guys. Because if we take the current coin, right, then the dpij will be a max dpij, right? And so it's going to be a dp. Okay, I is the, and then j minus coin, and then plus 1 in this case. Okay. And in the end, we simply return the dp, you know what, the n and the amount. That's so here, I mean, notice here. So first, this one is easy to understand. Basically, we just get the maximum from the two states, and we only do this because if we take the current coin, right, and then the previous state will be j minus coin, right? Because since we decided to take the current coin, so and then before taking the current coin, the previous state will be a j minus coin, right? That's why we do a j minus j to check here. Otherwise, this thing will become a negative, which will be invalid. It will be an invalid state. And here, right? That's the of course. So and then since we're taking one more coin, that's why we plus one in the end. This is easy to understand. And the 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 tricky part is this I here, you know, and you know this I here, right? Since since we can take the current ice coin as many times as we want, that's why this I means we have considered the current ice coin when we process this j. That's what we need, right? I mean, if you know about this 0, 0, 1 k knapsack problem, for that one, everything else is same. The only difference for the 0, 1 k knapsack is right here. So for this 0, 1 k knapsack problem, instead of a dpi minus 1 here, we do a dp. Instead of dpi here, we do a dpi minus 1. Why is that? Because when we calculate this dp I here, right, we don't want any state from dpi, because we know we want this dpi can only be taken at most once, right? And that's why for 0, 1 k knapsack problem, and we only when we calculate dp here, we only once we decide we take these coins, right? We will only consider the dpi minus 1 state, because we know that's the state we never we haven't seen we haven't taken any of the coins yet, right? But with complete knapsack problem, the difference is here. So that's the difference, because when we calculate dpij here, right, and we need to basically we need to consider the current state, the current DPI here, because it could be we have already taken some of the ice coins somewhere before, right? That's why we have to consider this the current ice state here, and then in the end we simply return the DP and amount, okay, and so, but how about this minus 1 here, right? How can we check if we can actually make up this exact amount here? That's what, remember, we initialize this to the max size, right? If we can't, let's say if we cannot even if we can't make uh let's say if we can't make any of the amount to the current uh amount. And what's gonna happen is let's say, so when we okay, so because we only initialize the 0 as the first state, right? Basically, everything from the DPI here, either from the DPI minus 1 or from this DPJ equals the coins, right? Basically, if there's no way we can get to the current amount with the coins, and this J minus coin will be basically will be never coming from the 0, 0, right? That's why and then this j minus coin will be the max value, and basically this both of these two values will be max value, and in the end our dpn amount will also be infinite, the max number. So basically, and when the number is from the max number, then we know, okay, there's no way we can get from 0 to the current amount, right? Because otherwise we'll get it. Oh, sorry. So here should be minimum. Sorry. Otherwise we would have like got a different number other than the max number if we can there if there is a path, if there's a path from j minus coin to the amount here. Okay. That's why for the and if yeah, so if dpn amount, sorry, not equal to the system max size, okay, else -1. Yeah, right. I think that's pretty much that should do it. Yeah, cool. So the test case passed. Let's try to submit it. Yeah, cool. So it's success, and yeah, basically this is like a very basic 2D knapsack complete knapsack problem. Basically, the outer loop is the item. In this case, is the coins, and the inner loop is the capacity in in the backpack problem. In this case, is the amount. And we have two cases. First one is we don't take the this uh, ice item. Second one is we take this ice item. But in this case, since it's a complete K knapsack problem, we have to consider the current ice problem. That's why we use the ice here instead of minus one. Okay, and in the end, we simply return this thing. And so you guys may have already noticed here. So the current dpij will only determines will only determine on the I minus one. Maybe here is even better because but here we will be it will be the I minus one here, right? So in this case we can actually compress this 2D DP array into one. So what we're doing here basically we can simply remove the first basically the first element, the first dimension, which is the loop, the for loop of the coins itself, right? So in that case, we can simply remove this the first dimension. So when we define the DP arrays here, all we need to define is one dimension, one size, or one dimension with the amount plus one, and same thing. Same thing. So here we're gonna have the DPJ in this case, right? So the DPJ still the same, right? DPJ means I mean to basically to the minimum cost to get to the J amount after considering the first ice coins. You can think it that way, yeah, because I'll show you guys what I mean here. So first, that even though we compress this DP from 2D to 1D, we still have to keep the same for loop here. Okay, the only difference is the mm, same 2D for loop, two for loops. So here we don't have to do it here because we compress the first element, so we can just simply remove this part, right? And then here, right here we just remove this one, J, okay, and then J and J, right? So here remove that, remove that, yeah, And I actually here, because so we can do a little bit improvements here. When we do the for loop here, instead of doing instead of looping through from 0 to j, right, as well. So we basically will basically skip that. We can just simply do a coins, right? We can start with coin here because we know when the j is smaller than coin, we'll just skip that. So why not just start looping from the coin itself? Okay, so here, uh, yeah, so yeah, okay, so that's I think this yeah this should just work. Let's try to run it again. Yeah. Yeah, cool. So, I mean, as you guys can see, so for this knapsack problem, we can always compress the 2D space to a 1D space. Okay, and in this case, it's this one. Oh, and one more thing. So this is like a complete 2D problem. Sorry, complete knapsack problem. So when it comes to the 0, 1 from 0, 1 knapsack problem, in order to compress the space complexity to 1D, we instead of so the only difference is the for the second loop here, second for loop here, instead of looping from small to the biggest, we need to loop through from the biggest to the smallest. Why is that, right? So why is that? Remember the when we write this dp here, dpij dpij, right? So and here is going to be the dpi minus 1. Remember? So for the 0, 1, this is the 0, 1. This is the 0, 1, right? So this is the state transition function for the 0, 1 knapsack problem. And if you guys remember here, so we need to rely on the I minus 1 case, right? Not the current ice state. That's why when we calculate on this the new level, the new ice, this current ice coins, when we start calculating, we want to make sure that the state we're using here is from the previous state, right? And if we're looping through the j here, the coins from smallest to the biggest here, by the time we calculate the j here, the state we're using will be would have already been calculated, right? Since we calculate the smaller number first, and the j minus coin smaller than the j, right? And basically that's wrong because in the 0, 1 backpack problem, we will only rely on the previously the I minus 1 state. That's why in order to do this, right, we can easy fix will be instead of looping through from the smallest to the biggest one, we reverse it. We loop through from the biggest to the smallest. That's why that will make sure every time when we use this the dpj minus coin, the value we use had not been calculated for the current I, which means it came from the I minus 1 state. Okay. Yeah. Okay. I think. Mm, yeah, I think that's pretty much it is I want to talk about for this classic knapsack problem, or you can call it the backpack problem. This is like just a little bit of variations instead of minimum, right? Instead of maximum, we do a minimum here. Everything else is the same. So for the maximum, we initialize if we want to get the max values, we initialize everything with 0. But in this case, it's the minimum. That's why we initialize with max size, right? And cool. Yeah, I think yeah, keep practicing the knapsack problem. I'll also do the same thing. And maybe I'll just upload a few more DP problem regarding this backpack problems. I think it's a very classic. It's a big category for the dynamic programming. I really hope everyone can understand and really master, right? Get familiar with this kind of problem. Okay, thank you so much for watching the videos, and I hope you guys like it and stay tuned. I'll see you guys soon. Bye bye.